Welcome to our latest video, Building a Time Machine. From the works of H.G. Wells to blockbuster movies like Back to the Future, time travel has captured the imaginations of people for decades. But what if I told you that the possibility of time travel might be closer to reality than we ever imagined? In this documentary, we will explore the cutting-edge theories in physics and uncover the potential solutions for building a time machine. From Einstein's theories of relativity to the latest research on exotic matter and space-time, we will delve into the scientific principles that could unlock the secrets of time travel. Join us as we embark on an exciting journey and discover the potential solutions for building a time machine, including wormholes, time dilation, cosmic strings, and tachyon. These solutions are grounded in cutting-edge theories in physics and have captured the imaginations of scientists and science fiction enthusiasts alike. But which one holds the most promise for building a time machine? In this documentary, we will explore each solution in depth, examining the scientific principles and engineering challenges that would need to be overcome to make time travel a reality. Building a time machine is no easy feat. It requires overcoming numerous scientific and engineering challenges, as well as discovering and understanding new phenomena in the universe. So put on your lab coats and grab your calculators as we delve into the fascinating world of time travel. Don't forget to hit the subscribe button and turn on notifications to stay updated on our latest videos. Step into the unknown, where the mysteries of time unfold. I am the timekeeper, and this is 2D time. Time travel has been a captivating topic in science fiction. But what if I told you that it might be closer to reality than we ever imagined? Today, we'll explore 4 potential solutions for building a time machine: wormholes, time dilation, cosmic strings, and tachyon. Let's get started. First up, wormholes. These theoretical tunnels through space-time were first introduced by Albert Einstein and Nathan Rosen in 1935. Their work on the Einstein-Rosen bridge laid the foundation for the concept of wormholes. Later, John Archibald Wheeler coined the term wormhole in 1957. To create or maintain a wormhole, one must overcome the tremendous forces at play. The basic equation for a wormhole is derived from Einstein's field equations of general relativity. The equation is G, mu, nu, plus lambda, lowercase g, mu, nu equals kt, mu nu, where g, mu, nu is the Einstein tensor representing the curvature of spacetime. Lambda is the cosmological constant. Lowercase g mu, nu, is the metric tensor. T mu nu is the stress energy tensor describing the distribution of matter and energy. And kappa is the Einstein gravitational constant. To keep a wormhole open, we need a form of exotic matter with negative energy density. One possible candidate for this exotic matter is the Casimir effect, which can help stabilize a wormhole. The Casimir effect arises from the quantum fluctuations of the electromagnetic field that exist even in empty space. To understand the Casimir effect, imagine 2 parallel plates placed very close to each other in a vacuum. According to quantum field theory, the region between the plates will contain fewer fluctuations of the electromagnetic field compared to the space outside the plates. This difference in the density of fluctuations results in a net force pushing the plates towards each other. Therefore, by using the Casimir effect, scientists speculate that it could be possible to stabilize a wormhole by placing 2 parallel plates very close to each other and using the resulting Casimir force to counteract the gravitational collapse that would otherwise occur in a wormhole. However, it is important to note that the concept of using the Casimir effect to stabilize a wormhole is purely hypothetical, and no such technology currently exists. Another way to build a time machine is by using time dilation, a concept from Einstein's theories of special and general relativity. In 1905, he published his special theory of relativity, which explained the behavior of objects at high speeds. This theory introduced the concept of time dilation, which states that time appears to run slower for an object in motion relative to a stationary observer. 10 years later, in 1915, Einstein introduced the general theory of relativity, which provided a deeper understanding of gravity in spacetime. The general theory of relativity describes how gravity is not a force, but rather a curvature of spacetime caused by massive objects. Time dilation occurs when an object is moving at a significant fraction of the speed of light, or is in a strong gravitational field. This means that time appears to run slower for the moving object relative to a stationary observer. In special relativity, the time dilation formula is delta t prime equals gamma delta t, which equals 2 delta t over square root of 1 minus v square over c square, where delta t prime is the dilated time, delta t is the proper time, v is the velocity of the moving object, and c is the speed of light. This equation shows that as an object approaches the speed of light, its time dilation increases and time appears to slow down even more. To illustrate this concept, imagine a spaceship traveling at high speeds relative to a stationary observer on Earth. According to the theory of relativity, time would appear to run slower for the astronauts on the spaceship compared to the observer on Earth. This means that when the astronauts return to Earth after their journey, they would have aged less than the observer on Earth. In summary, time dilation is a real phenomenon predicted by Einstein's theories of relativity. While time travel to the past remains a hypothetical concept, time dilation provides a way to travel to the future by experiencing time at a slower rate compared to a stationary observer. Our third solution for building a time machine involves cosmic strings, hypothetical one-dimensional defects in spacetime. Cosmic strings were first proposed by physicist Tom Kibble in 1976 during the study of phase transitions in the early universe. These structures are thought to have formed shortly after the Big Bang, as the universe cooled and underwent a series of phase transitions. While there is no direct evidence of their existence, they remain a fascinating area of research for theoretical physicists. These fascinating structures could potentially warp spacetime, allowing time travel. If two cosmic strings move parallel to each other at high speeds, they could create a closed time-like curve, enabling time travel. However, cosmic strings remain purely theoretical, and their existence has not been confirmed. Our final solution for building a time machine involves tachyons, hypothetical particles that travel faster than the speed of light. Tachyons were first proposed by Arnold Sommerfeld in 1904 and later named by Gerald Feinberg in 1967. Although tachyons have never been observed, their unique properties have made them a popular subject in both theoretical physics and science fiction. In the context of special relativity, the energy of a tachyon is given by E equals mc square over square root of 1 minus v square over c square, where E is the energy, m is the imaginary mass, v is the velocity of the tachyon, and c is the speed of light. This equation indicates that as the speed of a tachyon approaches infinity, its energy approaches zero, and vice versa. Despite their interesting properties, the existence of tachyons would violate causality, which is the principle that an effect cannot occur before its cause. This is because if tachyons could travel faster than the speed of light, they could potentially be used to send signals back in time, which would violate the laws of physics as we understand them. So how would one go about actually building a time machine? While we can't provide detailed blueprints, we can highlight some key challenges. For wormholes, we would need to harness the power of exotic matter to keep them stable. For time dilation, we would require a propulsion system capable of reaching near-light speeds or creating powerful gravitational fields. For cosmic strings, we would first need to confirm their existence and then find a way to manipulate their trajectories. And for tachyons, we would need to overcome the current limitations of physics to harness their faster-than-light capabilities. As you can see, building a time machine is not easy task. It requires overcoming numerous scientific and engineering challenges, as well as discovering and understanding new phenomena in the universe. Speaking of faster-than-light, the Alcubierre drive is a theoretical concept for faster-than-light travel that has captured the imaginations of scientists and science fiction enthusiasts alike. Proposed by Mexican physicist Miguel Alcubierre in 1994, the Alcubierre drive seeks to overcome the limitations of traditional spacecraft propulsion systems by creating a warp bubble around the craft. The warp bubble compresses space-time in front of the spacecraft while expanding space-time behind it. This creates a shortcut through space-time, allowing the craft to travel faster than light without violating the laws of physics. To understand the science behind the Alcubierre drive, we need to delve into the principles of general relativity. General relativity describes the curvature of space-time caused by massive objects, such as planets and stars. The Alcubierre drive is derived from the same field equations of general relativity that describe the curvature of space-time. These equations describe how we can manipulate space-time to create a shortcut between 2 points. However, to create the necessary warp bubble, we would need to harness exotic matter with negative energy density, just like in the case of wormholes. Exotic matter is a hypothetical form of matter that has negative energy density, which is not found in our everyday world. The exotic matter would allow us to create a warp bubble and compress space-time in front of the spacecraft, while expanding space-time behind it. This would effectively create a shortcut through space-time, allowing the craft to travel faster than light. While the concept of the Alcubierre drive is theoretically sound, the technology to create and control such a warp bubble is still far beyond our current capabilities. In addition, the amount of energy required to create and sustain the warp bubble would be enormous, and the effect on the space around the craft could be significant. It's important to note that while the Alcubierre drive remains a fascinating area of research, the technology to make it a reality is still in its infancy. Nonetheless, the potential applications of the Alcubierre drive in space travel and exploration are vast, and it remains an intriguing concept for physicists and engineers alike. As exciting as the prospect of time travel may be, it's important to acknowledge the potential challenges and implications it brings. Paradoxes, such as the famous grandfather paradox, pose significant questions regarding the nature of causality and the consequences of changing the past. Additionally, the energy requirements for creating wormholes, warp bubbles, or manipulating cosmic strings are astronomically high, far beyond anything our current technology can produce. Ethical considerations also come into play, as time travel could be used maliciously or irresponsibly, leading to unforeseen consequences on a global scale. Despite these challenges, the pursuit of time travel has led to countless advancements in our understanding of the universe. From theoretical physics to cutting-edge engineering, the quest to unlock the secrets of time has brought together some of the brightest minds in human history. While we may not be able to build a time machine in the foreseeable future, the knowledge we gain from studying these complex theories can help us better understand the cosmos and potentially lead to breakthroughs in other fields. Who knows? Perhaps one day we'll unlock the key to time travel, allowing us to explore not only the vast reaches of space, but also the intricacies of time itself. Astrophysicists play a critical role in the study of time travel, as they work tirelessly to unravel the mysteries of the universe. Their research encompasses everything from celestial mechanics and cosmology to the study of exotic phenomena like black holes, dark matter, and dark energy. It's the work of these brilliant scientists that will ultimately determine if time travel is truly possible, and if so, how we can safely harness its potential. While we may be a long way from hopping into a DeLorean and traveling through time, the study of wormholes, time dilation, cosmic strings, and tachyons have provided us with a deeper understanding of our universe and its underlying principles. The pursuit of time travel has fueled the imagination of scientists and storytellers alike, inspiring countless works of fiction and sparking curiosity in the hearts and minds of people around the world. So, until we crack the code on time travel, we can still enjoy the thrilling adventures of Marty McFly, Doctor Who, and the many other time-traveling heroes of our favorite stories. Thank you for joining us on this journey through the science and theory of building a time machine. If you enjoyed this video, don't forget to like, share, and subscribe for more amazing content. And remember, the future is always just a moment away.